Today I'm gonna talk about three of my favorite things: JavaScript, Unicode, and 90s gangster rappers. So this is me. Yeah, I'm Mathias. I have a Twitter account, as you can see. So if you happen to have any questions at all during the talk, feel free to send me a message on Twitter, and I'll make sure to get back to you. Of course, there'll be time for questions afterwards as well. And both as part of my job, I work for Opera Software, by the way, in developer relations. Both as part of my job and in my spare time, I like to collaborate on various open source projects. I have some of those projects of my own, and one of those is Unicode.js. Now, if you don't know what Unicode is, well, it's basically what you can see here. Unicode is the name of the algorithm that converts an internationalized domain name, so a domain name containing special non-ASCII Unicode characters, like the E with the accent there, into its pure ASCII form. And this is required for domain names because at the DNS level, only ASCII characters can be understood. So Unicode is basically a clever hack for domain names that allow us to use these special characters in domain names anyway, even though DNS really doesn't support these characters directly. So the Unicode standard defines the algorithm to convert from the thing you see on the left side to the right side and the other way around. That's Unicode, basically. So when I learned about Unicode, I figured, hey, there's this whole specification dedicated to this thing, and it lists all the steps you need to perform in the algorithm. So it should be fairly simple to port this to JavaScript, right? And boy, was I wrong. There were a couple of things that I didn't know about JavaScript, the language itself. And those things came to bite me in the ass when I was working on this project. So basically, that is what this talk will be about, the weird behaviors that I run into that are part of the JavaScript language itself that make dealing with strings sometimes a bit harder than you would expect. But first, before we get started with that, does anyone know who this guy is? He's black, but not that black, so yeah. No one? Come on. You can shout. Jay-Z, of course, everyone knows it's Jay-Z. He's a famous American rapper. But a little known fact about him is that at some point he decided to write a JavaScript program. But at the end of the day, he had written a song about his frustrations with the language instead. You may actually have heard this song before. It's called 99 Problems. Now, don't get me wrong, even though I'm making fun of JavaScript here, it's absolutely my favorite programming language, and I think it's just a fact of life as a programmer that you're just going to be surprised and, well, frustrated every now and then. Every programming language has its weirdness and its quirks, and that's why we have websites like phpwhatthefuck.org, which neatly documents all these weird behaviors in the PHP language, and also we have whatthefuckjs.com, which does the same thing for JavaScript. And sure, these things look weird at first, but all of these things can really be explained if you just read the specification, or for PHP, if you view the documentation, or even view the source code. But even then, even though everything can be explained, still, if a particular behavior of a language is confusing to a lot of people, then that becomes a bit of a problem. And that's why I go ahead and say that JavaScript has a Unicode problem. The way JavaScript handles Unicode is just very surprising, to say the least. And before we get into the details of all that, we should make sure we're all on the same page when it comes to Unicode. So I'm going to tell you the absolute minimum that you need to know about Unicode in order to be able to deal with JavaScript strings correctly, okay? Nothing more. So it's easiest to think of Unicode as kind of like a database that maps any symbol that you can think of to a unique number for that symbol called its code point, and also to a unique name for that symbol. And this seems fairly simple, and it is, but the main advantage of this is that this way you can refer to any specific symbol without having to use the symbol itself. So for example, Unicode maps the Latin capital letter A to the code point U plus 0041. Now this is a hexadecimal number, so not a decimal number. It's actually the number 65 if you were to put it in decimal digits. Now code points are usually formatted this way. So it starts with the U plus prefix, and then it's followed by at least 4 hexadecimal digits. And as you can see, if you don't really need 4 hexadecimal digits, usually it gets 0 padded, so that there's at least 4 digits anyway. Now another example is the Latin small letter a. This is a completely different symbol, so it gets its own unique canonical name and its own unique code point for that symbol. it's as simple as that. I think you start to get the idea now. Each symbol in Unicode simply gets its own code point and its own name. Now there's a lot of weird stuff in Unicode as well. For example, there's a snowman symbol. I'm not sure why you would ever need it, but it's there if you want to use it. The code point is 2603. So there you have it. And then there's everyone's favorite Unicode character, the pile of poo. Yes, that is the actual canonical name for the symbol in the Unicode standard. I would have loved to be there at the committee meeting when this was decided. But anyway, as you can see, the code point for this symbol is 1F4A9, which is 5 hexadecimal digits. It's more than 4. So at this point, you may be wondering what the highest possible code point value is, or how many code points there are in total in Unicode. Well, the possible code point values range from 0 to 10FFFF. So in decimal digits, in decimal numbers, that's over 1.1 million possible symbols. Now, to keep things a little bit organized, Unicode divides this range of code points into 17 planes that consist of about 65,000 symbols each. Now, the first one of these planes is called the BMP, or the Basic Multilingual Plane. And it's probably the most important one of them all because it contains all the most commonly used symbols. In fact, if you're writing a text document in English or Finnish, you probably won't need any code points at all that are not part of the BMP. Now, because the Basic Multilingual Plane contains all the most important and popular symbols, I like to refer to it as the notorious BMP. Now, anyway, just like any other plane, it contains about 65,000 symbols. That leaves us 16 other planes, just like this one, that total up to about 1 million code points. So the planes that these code points belong to have a group name. They're called the supplementary planes or the astral planes. So similarly, whenever someone is talking about an astral symbol or an astral code point, it just means a code point that belongs to one of those other planes, not the BMP. Now, these astral code points are pretty easy to recognize because you need at least 5 hexadecimal digits to represent them. Now, one example of where Unicode is really useful is in the context of character encodings. Now, character encodings define how strings of text end up getting stored as sequences of bytes. So thanks to Unicode, all that a character encoding needs to do is just provide that mapping from a Unicode code point to a sequence of bytes for that code point. And here's a list of encodings that fully support Unicode. You may have heard of some of these before. So full Unicode support in this context means that they can encode or decode any Unicode code point value. Now, this table shows the number of bytes that each code point and each encoding requires for each code point. So one of these encodings is a fixed width encoding. Any ideas which one that is? Well, it's not this one. It's UTF-32. That was too quick. Okay, so UTF-32 has a fixed width of 4 bytes for any code point at all. It doesn't care what code point you're trying to represent. It will always take up 4 bytes of space. And that is nice and consistent, but it also takes up a lot of storage space. So all the other encodings that you see here, they're a bit more optimized in a way. UTF-16, for example, it uses 2 bytes for any BMP code point, but it will need twice as many. It will need 4 bytes for any astral code point, as you can see here. Now, whenever you have a choice, you should always try to use UTF-8 to encode your data. And the reason for that is UTF-8 is optimized for text documents. Like, as you can see there, some code points will only take up a single byte in UTF-8, and those are the ASCII symbols. This also means that UTF-8 is backwards compatible with ASCII, so any text document from the 70s that was encoded and saved as ASCII, it can perfectly be decoded as UTF-8, and it will be exactly the same document. So it's backwards compatible. And also, as you can see, other BMP symbols will take up 2 bytes, so it's 1 or 2 bytes for any BMP symbol. And then astral symbols, well, it depends. It takes up 3 or 4 bytes, depending on where the code point lies exactly. Now, if you want to find out more about these encodings, it's very tempting to just Google for the name of the encoding, like I did here, and then you'll usually find a document like this. This is an RFC, or a request for comments document, published by the IETF. And this is a document that originally defined how UTF-8 was supposed to work. It's very old. Now, the problem with that is most of the time you don't really need to know how the encoding was originally designed. It's much more interesting to see how they're currently being implemented and how the encoding is being used in the real world. So don't look for these documents. Don't just Google the name of the encoding. Instead, you should be looking at the encoding standard. So rather than a theoretical design document, like the RFCs are, this document is based on existing implementations of the encoding in web browsers and in other software. So try to look it up here instead. And yes, sometimes there is an actual difference. For example, for UTF-8, originally it was defined to support code points up to 7 FFF, which is, you know, a very, very high value, and Unicode standard doesn't even contain that many code points. So implementations in the real world don't even support that kind of thing. Anyway, let's get back to the issue at hand, Unicode in JavaScript. So now that we have a basic understanding of Unicode, let's see how that applies to JavaScript strings. You may have seen things like this before. In a string literal, you can have a backslash followed by x followed by 2 hexadecimal digits. And now that we know about Unicode, it's easy to see what these digits refer to, right? These digits refer to a Unicode code point. So this is in fact the code point 4.1 followed by the code point 4.2, 4.3, which is another way of using the string ABC in all caps. Now, this can be useful sometimes for certain strings. For example, if there's a character that is hard to type on your keyboard, or you want to avoid encoding issues when the file is saved using an encoding that you did not intend to use. For example, here I'm using the copyright symbol and the accented E character. So sure, these escape sequences are fairly useful, but this is still kind of limited. We can only use this for code points up to FF because we're limited to just 2 hexadecimal digits at a time. Now, luckily for us, there's another type of escape sequence called the Unicode escape sequence. And this starts with a backslash followed by U followed by 4 hexadecimal digits. That's a bit better. Now we can also escape the code point 2661, for example, which turns out to be the white heart symbol in Unicode. So sure, this is useful. We can use this for all the BMP code points. But what about all those other code points? What about the Astral code points and the Astral symbols? How do we escape those if we can only use 4 hexadecimal digits at a time? So another way of phrasing this question is, what about our friends, the pile of poo, and equally important Astral symbols, of course? Well, the answer is we can actually represent them, but it's kind of complicated. In ECMAScript 6, or ECMAScript 2015, as it's been called nowadays, I'll just continue calling it ECMAScript 6. This is what you can do. It introduces yet another type of escape sequence called the Unicode code point escape. It starts with a backslash followed by U followed by braces. And between these braces, you can use as many hexadecimal digits as you like. And of course, you only really need 6 to represent any Unicode code point. So this gives you an easy way of representing any symbol at all, purely based on its code point. It works for any code point at all. Now, if you need something that works today in all browsers and that is backwards compatible with ECMAScript 5, you're stuck with using this thing called surrogate pairs. And this is kind of a pain in the ass. In this case, each of the individual escapes represents the half of a surrogate pair. And the surrogate halves combined together, they form a single symbol. So this is kind of weird. And another thing that's weird is that the 2 code points that are being used in the escape sequences, they don't really look anything like the original code point, which is 1F4A9. It's hard to see which symbol is actually being represented here. Now, there are formulas that can be used to calculate these 2 surrogate halves that you need to use based on the original Astral symbol and the other way around. Here's a JavaScript implementation of that. Now, you don't need to remember this exact implementation, of course, but apparently you do need to know that this sort of thing exists if you want to deal with strings in JavaScript correctly. Now, anyway, this whole concept of using just a single escape sequence for BMP symbols, but then requiring 2 separate escapes for Astral symbols, that's a bit confusing. And it has lots of annoying consequences throughout the entire JavaScript language. Let's say, for example, that you want to count the number of characters in a string. My first thought would probably be to just get the length property of the string, right? So if you have a string with the capital letter A in it, and then you get its length, it will tell you the length is 1, which makes sense because there's one symbol there. And you can also explain this by rewriting the string using nothing but escape sequences. And then you can count the number of escapes, and then you see, okay, there's one escape sequence there, so it makes sense that the length is 1. In these examples, the length property of the string happens to reflect the number of characters in the string. But this is not always the case. And that's one thing that really surprised me. Let's try some other symbols here. So these symbols look a bit different, but almost the same. This is the mathematical bold capital letter A and the mathematical bold capital letter B. They're different symbols, so of course they get their own code points. And as you can see, these code points are astral code points. And because of that, they now get a length of 2 instead of 1, which is kind of surprising, even because there's only one symbol there, really. And this is because JavaScript exposes these separate surrogate halves as if they were separate characters, almost. And this is really confusing for us because we are just human beings and we generally think in terms of Unicode characters rather than surrogate pairs. So similarly, a string containing only the pile of poo has a length of 2 in JavaScript. And for the Americans out there, there's a very obvious joke to be made here. But instead, I'm just going to move on and show you a real-world example of where this actually breaks stuff. So this is Twitter not too long ago. As you know, Twitter allows 140 characters per tweet, and they have their neat counter on their website that tells you how many characters you have left. And their backend doesn't care what kind of symbols you use. So you can use astral symbols, and it will still count only as one symbol. However, at some point they had a bug in their counter, and for every astral symbol that you entered, the counter would decrease in steps of 2 instead of 1, as you can see here. So because of this bug, it was only possible to tweet up to 70 piles of poo at a time. It was a terrible, terrible, terrible bug. Now, another example is the countable chess, which is a JavaScript library that counts how many words and paragraphs and characters you use in a text area, and then it displays those numbers somewhere else on the page. It's just an example. I saw this demo page for it, and the first thing I tried was, of course, to enter a pile of poo. And, well, unsurprisingly, it counted it as 2 separate characters. So I filed a bug, submitted a pull request. It's been fixed now, but this is just an example. This is really an honest mistake to make. But the bottom line is, if you're writing a JavaScript library or you're writing any JavaScript code at all that deals with strings, which you probably all do, and especially if it deals with user input, you have to make it work with all symbols, not just with BMP symbols. You don't really have the choice because you never know what kind of symbol your user will enter. And the easiest way to verify that you're doing everything correctly is just to do what I did. Just throw some piles of poo in there and see what happens. So this is kind of what it felt like to enter that pile of poo character. You know, I just almost knew that something would go wrong. Yeah, so getting back to the problem at hand, how can it be done? How can we accurately count the number of code points in a JavaScript string? Well, one thing you could do is you could depend on a third-party library. And Unicode.js, the library that I mentioned earlier, it has these utility methods that it uses internally, and it exposes those so that you can use them in your own scripts if you would like to. And it has a UCS decode method that takes a string and it returns an array of code points, one item for each code point in the string. So if you run the string to there and then get the length property of the resulting array, that will give you a more accurate result. Of course, this is not really ideal because now you have a dependency just to be able to count the number of symbols in a string, which is probably not what you want. Luckily, in ECMAScript 6, there will be another way to solve this without any libraries at all. You could do it this way. You can use the new array.from method and then pass in the string there. And then internally, this will use the new ES6 string iterator, which is a separate new feature. And the string iterator is designed to iterate over each code point in the string rather than over each code unit, which is what the surrogate halves would expose. So this will give exactly the same result without using any libraries at all. A similar solution also in ES6 is to use this. Here we're using the spread operator to do basically the same thing as in the last slide. It's just a bit more concise, but also maybe a bit more cryptic. I don't know. Anyway, none of these solutions is really super efficient. If you want a very efficient solution, you should use a regular expression, remove all the astral symbols from the string, replace them with a single ASCII symbol, and then get the resulting length. That's the best solution, and that's also how Twitter solved the problem, by the way. We'll talk about regular expressions later. Now, another thing I did is I made a tool that takes a string as input, and then it shows the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, except that the output is valid JavaScript, which is sometimes more useful. With this tool, it's really easy to tell what kind of symbols a string contains exactly, even if the symbols are non-printable or just white space characters. So what I've been telling you so far about dealing with astral symbols, that's something you have to do all the time. You don't really have a choice because you never know what kind of user input you will be getting. But depending on your use case, that may not be enough. There might be other things that you need to do. And here's an example. Well, we know how to count code points correctly now, but if we're being really pedantic, then counting the number of symbols in a string is even more complicated. Here, JavaScript seems to be telling us that these two strings are different, but visually there's no way to tell, right? So what is going on here? Well, I took these two strings and I just copied them into the tool that I just showed you, and this is what I got. So as you can see, the first string uses a single character with code point F1 to represent the N with the tilde on top of it. The second string, however, has a separate N character followed by the code point 0303, which is a combining tilde. Unicode has a lot of these combining marks, and the way they work is they basically just get applied to the previous character in the string. And this allows you to form combinations of different characters with accents and stuff like that. So this is why visually we're getting the same result, but if you look at the code points that are being used in the strings, they're not the same at all. And also the first string has a length of 6, the second string has a length of 7, and we can see why now. But really, as a user, we don't really care about this difference. If you count the number of symbols in these strings, we expect a result of 6 for both strings. So how can we make that happen? How can we get that expected result both times? Well, ECMAScript 6 has a solution for this as well. It's called Unicode normalization. And it's now available as a built-in method on the string prototype. So you can just take any string at all, call the normalize method on it. You can even pass in a normalization form. There's 4 options there. You can look it up in the Unicode normalization standard if you like. I'm using NFC here, and that will basically take care of these lookalike characters like we saw earlier. And of course, after that, we still have to account for the surrogate pairs and the astral symbols, just like we did before. And then finally, the result will be even better than it was before. Now, is this perfect? Well, it depends. Again, if you need to support things like this is a string with lots of combining marks applied to the same character. So visually, I count 9 different symbols here, but each symbol has at least 20 different combining marks applied to it. That's why it looks so weird. So how many symbols does our pedantic function count here? Well, I count 9, but even our most pedantic function counts it as 116, and it's easy to see why. So again, if you need to support this kind of thing, it's probably best to write a complex regular expression that removes all these special characters, all these combining marks from the string, and then gets the length just like we did before. But again, we'll talk about regular expressions later. Here's another thought exercise, how to reverse a string in JavaScript. It sounds really simple, right? So how hard can it be? Well, this is a fairly common solution to the problem. You just take the string, you split it up into an array of characters, then you reverse that array, and then you glue it back together. And indeed, that seems to work in a lot of cases. If you try to reverse the string ABC, you get CBA, which is what you expect. Let's try another one. Let's try to reverse mañana, where the N and the tilde is a single Unicode code point. Again, this works as expected. Let's try the other mañana, where the N and the tilde are separate characters. Well, now the tilde suddenly gets applied to the A instead of to the N, which is probably not what you would expect. And when you try it on an astral symbol, which as we now know consists of 2 surrogate halves in JavaScript, the reversed result is completely unusable because the surrogate halves are still there, but they're in the wrong order. So you won't even see the symbol that was there originally in the string anymore. This is a form of data loss. So even something as seemingly simple as reversing a string becomes really tricky in JavaScript, especially if you need full Unicode support. Now, luckily for us, a brilliant computer scientist named Missy Elliott came up with a bulletproof algorithm that accounts for these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by swapping the position of any combining marks with the symbol that they belong to, as well as by flipping the surrogate pairs before further processing the string, just like we did before, all those issues are avoided successfully. So thank you, Missy. And I've built a JavaScript library called srevert that does just that, using that algorithm. So if you ever need to reverse a string in JavaScript, you can use it. Anyway, those were just some examples. Of course, it's not very common to actually need to reverse a string in JavaScript. I just want to make you think about this behavior because it all boils down to the same problem, really. And this behavior affects other string methods too. So for example, string.fromCharacter code allows you to take a code point, so you can pass a number to it, and then it will create a string based on that code point. But it only works correctly the way you would expect it to for BMP code points. As soon as you pass an actual code point, you will still get a result. It won't throw an error or anything, but it won't be the result that you expect. Now, the solution here is to actually pass separate arguments. You need to pass 2 parameters there, and that means you also need to calculate the surrogate halves individually yourself. This means you need to implement those formulas that I showed you earlier. And of course, that's a pain in the ass. You don't want to do that. Another solution is, of course, to use a third-party library that does the conversion for you. So then you can just pass in the original code point and you don't have to deal with the formulas yourself. But again, this is not ideal because now you have more code just to turn a code point into a string. It shouldn't be this way. And that's why ECMAScript 6 introduces a new method called string.fromCodePoint. It does kind of the same thing as string.fromCharacter code, except that this one actually works, even for astral symbols. Now, another example is string.prototype.characterAdd. If you use characterAdd to retrieve the first symbol in the string containing the pile of poo character, you'll only get the first surrogate half instead of the whole symbol, which may not be what you expect. Now, there is no solution for this in ECMAScript 6, but there is a proposal on the table for ES7. There could be a method on the string prototype named add, for example, and then it would work similarly to character add, except it would automatically deal with full symbols instead of with surrogate halves whenever possible. It would group them together for you. Now, character code add has a similar problem. If you use character code add to retrieve the code point of the first symbol in the string with a pile of poo character, you'll get the code point of the first surrogate half, not the code point of the pile of poo character. ECMAScript 6 solves this by introducing string.prototype.codePointAdd, which again does the same thing as character code add, except it also automatically groups these surrogate pairs together the way you would expect. Now, these methods are available in most browsers, in the latest versions of most browsers, but even if they aren't, and if you want to support older browsers, you can use the polyfills that I linked to at the bottom of the slide here. And that way it works even in IE6 if you still need to support that. Here's another example. What if you need to iterate over all the symbols in a string? Well, in ECMAScript 5, you would have to write a lot of boilerplate code just to account for surrogate pairs. So you want to loop over every symbol in the string, but whenever there's a surrogate pair, you want to group those two together and treat them as one single unit. And that's how you would do that in ES5. And no, the code is not even exactly complete yet. There's even more code that you need for this, but I couldn't fit it on my slide. Anyway, in ECMAScript 6, this becomes really easy. You can just use the new for_of construct, which is an iterator, and that will again use the internal string iterator, which is the other new feature in ES6 that I mentioned before. This string iterator deals with whole symbols instead of surrogate pairs automatically. And that means you can just iterate over every symbol in the string like this, with just a few lines of code. It's so much simpler. Now, anyway, these were just some examples, but remember, this behavior affects pretty much all string methods, so you should be really careful when using them. And all of this is really unfortunate, but as Tupac would say, that's just the way it is. Some things will never change. Now, let's talk about regular expressions. the dot operator in a regular expression only matches a single character, as you know. But because JavaScript exposes these surrogate halves as if they were separate characters, the dot operator won't ever match an astral symbol. So in this case, I would expect foo.bar to match the string with foo pile of poo bar, but it doesn't. So let's think about that for a second. What regular expression could we use to match any Unicode code point at all? So we can't use the dot operator. We've ruled that one out. Because it wouldn't match line breaks either, and it also doesn't match astral symbols as we've demonstrated. So we can solve the line break problem by using something like this. So by matching all white space characters and all non-white space characters as well, you basically match all characters, but you still wouldn't match astral symbols because as far as JavaScript is concerned, those are two separate characters. So any ideas? What would the regular expression look like to match any Unicode code point whatsoever? Yeah, me neither, but apparently it looks like this. So yeah, this can be explained, hold on. So the first part of the regular expression matches any BMP symbol that does not store a surrogate pair, and then the second half of the regular expression matches a surrogate pair or an astral symbol. In JavaScript, it's also possible to have a string that contains lone surrogates, so a surrogate that doesn't have a pair, that doesn't form a pair. Technically, they should be invalid, but JavaScript still supports it, and this regular expression would match that as well. Now, of course, this is not the kind of regular expression that anyone would like to write out by hand, let alone maintaining it. So that's not what I did. I actually used a JavaScript library called regenerate to generate these regular expressions for me. And this is how I did that. So that's the one line of code that I used to generate that last regular expression. Basically, you start a new regenerate instance, you add the whole range of all Unicode code points to the set, and then you call toString, and then you get a string that can be used as part of a regular expression literal. The reason it returns a string is so that it can be used as part of a build script. That's really what regenerate was created for. The idea is to generate a complex regular expression, then save it to a file, and then use that as part of your library. Here's a slightly more complex example, perhaps. So again, we create a new instance, we add the whole range of Unicode code points to the set, and then we remove the range of symbols based on their string values, from capital letter A to lowercase z. Then we remove a single symbol based on its code point value, in this case, the pile of poo. And then we call toString. So can anyone predict what this regular expression would look like? Yeah, again, me neither, but you don't want to and you don't need to. The main idea is that it's much easier to just write those 5 lines of code that you see there compared to writing that regular expression. Imagine if you have only this regular expression and you have to remove one more astral symbol or even a BMP symbol from the set. It would be a pain in the ass to do it, and it would probably take you a very long time. But it would be much easier to just change the 5 lines of code, remove just one more symbol from the set, and run the build script again. So my advice, never try to write this by hand. Use a tool for it, like regenerate. Here's one more example. Let's say you need a regular expression that matches all the Greek symbols in the Unicode standard, for example. Unicode has special data tables for this, and categories and properties and scripts and all that kind of stuff. So let's say you want to turn that into a regular expression. Well, you can use these modules on NPM that contain all this Unicode data for any given Unicode version. So here we're getting an array of all the Greek symbols with all the strings in there. We store that in as the variable symbols. Then we pass that to regenerate, create a set based on that array, and then we call toString on that, and that gives us this regular expression. Again, not something that you would enjoy writing by hand, but the script, those 4 lines of code, that's really easy. It couldn't be easier, really. Now, you may have noticed that I'm using the data for Unicode version 6.3 here, but Unicode version 7 has been out for a while. So imagine that this is some old script that you used once upon a time, and now that Unicode version 7 is out, you want to update your regular expression to use the latest Unicode data. Well, it would be a pain to go start from scratch and write that regular expression by hand and try to update it manually. But now all I need to do when I have a script like this is just change a single line of code in the script like this. So changing that regular expression manually would have taken a long time, but now all I had to do was change the version number of Unicode that I wanted to use there in the second line, and then run the script again, and just like that, an up-to-date regular expression comes out. Now, getting back to our problem with the dot operator, good news, because ECMAScript 6 kind of has a solution for this. There's a new flag for regular expressions, the U flag, which stands for Unicode, and if you use it, the dot operator will automatically match whole code points instead of surrogate halves, just like you would expect. So my advice is always use the U flag for new regular expression that you create. Here's another example. As you probably know, in regular expression character classes, you can use ranges. In this case, for example, we create a range from the lowercase letter a to lowercase letter c. So that would match A, B, and C, right? Yeah, this makes a lot of sense. So similarly, you might expect this regular expression to match the pile of poo, the flexed biceps, and the dizzy symbol. But unfortunately, it doesn't really work that way. In fact, you would get an error on the very first line of code here. So what is going on there? It tells you the regular expression is invalid, the range is out of order in the character class. But why does this happen? Because, I mean, this is the order the code points are defined in the Unicode standard, so they're in the right order. So what is going wrong here? Well, as far as JavaScript is concerned, this is what that regular expression looks like. Remember, it kind of exposes these surrogate halves as if they were separate symbols. So instead of the range that you intended to create, it now tries to create a range between the one surrogate for the first character and the first surrogate for the last character, which is not the range that you wanted. And because the first number is higher than the second one, this is, of course, an incorrect range. That's why you get the error. So how can we make this work? Once again, in ES6, it's really easy. You just add the U flag to your regular expression, and that magically makes it work the way you would expect it to. Now, if you need something that works today in existing environments in ECMAScript 5, you're back to using something like regenerate. You could do something like this, where you manually create a regular expression, and apparently it will look like this. But you don't want to have to do this for every regular expression that you write. You don't want to have to create a special build script all the time. So a better solution is available now. I worked on a transpiler called regexpoo, and it allows you to write your code using the ES6 syntax. So you can use the U flag on your regular expressions, and then you can feed it to my transpiler. It will look for any regular expression that you use that makes use of the U flag, and then it will rewrite those regular expressions so that they're equivalent, but without using the U flag. And regexpoo is also part of Tresor. So if you're already transpiling your code at all using Tresor, or even using Babel, or 625 as it used to be called, well, good news, because then you can already start using these regular expressions with the U flag. It will automatically be transpiled into equivalent ECMAScript 5 code. So you can start using all these things today. Now, in summary, it's pretty obvious that JavaScript has a bit of a Unicode problem, but rather than complain about it like Jay-Z did, I think we should be doing this instead. Oh yeah, we should just deal with it and work around these issues, because really it's not that hard. I think the main problem is not that it's hard or that people don't want to fix it. It's just that a lot of people don't know about these issues because the behavior is just so surprising. Now, if every one of us would just submit a pull request today that adds a pile of poo to the unit test for any JavaScript library at all that you're using, or that maybe that you've built yourself, I think collectively we could discover lots of bugs, and that would be a good first step towards getting these bugs fixed. Because I think the problem is not that developers don't want to fix these issues, it's just that they don't know about them. So I would say go forth and spread piles of poo, or something like that. Anyway, the link to the slides is there at the bottom. There's also a blog post that has all the info that I mentioned here, and I'd like to thank you for your attention. Cheers.